Good afternoon, students. In the last class, we were discussing about the chemical bonding chapter. Chemical bonding. We were discussing about the chemical bonding chapter, chemical bonding topic. Out of in this topic, we have discussed about the Lewis-Boson structure and valence bond theory as well as the Bsc theory. So, while studying the valence bond theory, one term we have studied that is hybridization. Hybrid refers to the mixing of the two different organisms or mixing of the two different matters. It forms a new matter that is nothing but the hybrid matter. Here hybridization refers to mixing of two different orbitals. Two different orbitals with different energies. With different energies. So we know that during the formation of the molecule, single bond will be formed, a double bond will be formed, a triple bond will be formed. That thing we have studied. How is single bond or the double bond or the triple bond is formed? That one is explained using the hybridization term. One main thing which the element which has to undergo the hybridization is mainly the orbital should contain, valence orbital containing unpaired or paired electrons in it. Unpaired electrons are paired electrons, and these paired electrons have got different energy levels. And these orbitals undergoing mixing. Mixing is nothing but the hybridization. It undergo mixing of the orbitals with the different energies. That mixing is term, or the combination term is called as a hybridization. After the hybridization or after the mixing of the orbitals, it forms new orbitals. That new orbitals have got same energy. It has got same energy in it. Unpaired electron or the paired electron should be present in the valence orbital. That unpaired electron and the paired electron present in the valence orbital undergo mixing. During the mixing, that process is nothing but the hybridization process. It undergo hybridization. During the hybridization, after the hybridization, it forms the new orbitals. That new orbitals have got a similar energy. After getting the same energy of one atom, another valence electrons of another atom undergo overlapping. It undergo overlapping. So another valence electrons, another atom which containing the valence electrons undergo overlapping with the hybridized orbital. It forms the bond. That bonds are nothing but the covalent bond formation. That bond is nothing but the covalent bond formation. We know that covalent bond formation, hybridized orbital with the same energy overlapping with the another atom with the valence orbital, it forms a new bond. That new bonds are nothing but the covalent bond. And this covalent bond, it has got two two types. One is a sigma bond, another one is a pi bond. Sigma bond is a stronger bond. Sigma bond is a stronger bond. Pi bond is a weaker bond. Sigma bond is a stronger bond. Pi bond is a weaker bond. Why it is considered as a stronger bond and a weaker bond? It depends upon the overlapping. Sigma bond mainly formed due to the head-on overlapping. Pi bond is formed due to the sideways overlapping. If you consider these two are the orbitals, if the overlapping is taking place like this one is nothing but the head-on overlapping. If the idunu head-on overlapping anta helidre ee reeti agutte, but two sigma bonds are not possible. Like this it is formed. One is sigma bond formation, another one is a pi bond formation. See, breaking of this bond is difficult, breaking of this bond is easy. So the sigma bond is a stronger bond and the pi bond is a weaker bond because of the sideways overlapping. This one is a head-on overlapping for the formation of the sigma and the pi bond. Most of the times write the difference between the sigma bond and the pi bond question may ask you for your final examination. Now, during the formation of the covalent bond, I said sigma bond and the pi bond is formed. So, during the formation of the sigma bond and the pi bond, atoms undergo hybridization. It undergo hybridization. Hybridization is nothing but the mixing of orbitals with the different energy. Mixing of the orbitals with the different energy is nothing but the hybridization. Okay. Now, depends upon the hybridization. Hybridizations are classified, or the types of the hybridizations are Sp3 hybridization, Sp2 hybridization, Sp hybridization, Sp3 dehybridization, Sp3 D2 hybridization. See, all these types of hybridization you are going to study in this hybridization topic. Sp3 hybridization, Sp2, Sp hybridization, Sp3D and Sp3D2 hybridization. And all these hybridizations are very important for your examination work point as well as for the competitive part. Hybridizations are very important. Now, let me start with the first type of hybridization, that is Sp3 hybridization. In the Sp3 hybridization, one s orbital, one is a natural number I am writing, I am not writing the principal quantum number, one s orbital plus 3 p orbital. One s orbital and 3 p orbital combining to give Sp3 hybridization. Now, if you count the number of hybridized orbitals are 1s3p, so total 4 orbitals are present. If 4 orbitals are involved in the bonding formation or in the hybridization formation, the geometry of the molecule will be tetrahedral. Geometry of the molecule will be tetrahedral. Because 4 corners will be there, so the geometry is a tetrahedral shape. Later on we will study, and it depends upon the tetrahedral. You can write the bond angle. It is like 109 degree 28 minutes. 109 degree 28 minutes is the bond angle in the tetrahedral geometry. And in the Sp3 hybridization, for about 25% of S character plus 75% of P characters are present. 25% S character and 75% P character will be present. Now, let me write the orbital diagram. S orbital, we know that it is a spherical in shape. 3p orbitals are present. 3p orbitals are present. Let me write it like this. One dumbbell, x axis, another dumbbell, y axis, one more dumbbell, it is in the z axis, px, py and the pz. It is get combined, mixing of the orbital taking place. It forms a Sp3 hybridized orbital Sp3 hybridized orbital. It is nothing but the Sp3 hybridized orbital. So it forms a tetrahedral geometry. Tetrahedral shape will be forming, and the bond angle is for about 109 degree 28 minutes. Now let me take an example for the Sp3 hybridization. Let me take an example for Sp3 hybridization. Formation of first one, formation of CH4, formation of methane molecule. Now let us write the electronic configuration. Carbon, atomic number of the carbon is 6, so the electronic configuration is 1s2, 2s2, 2p2. 2s2, 2p2 is considered as a valence shell. So if you write the box diagram for the valence shell, 2 electron in the 2s orbital and 2 electron in the 2p orbital. See, in the molecule CH4, for one carbon atom, 4 hydrogen atoms are required. 4 hydrogen atoms are required means from carbon to hydrogen, bond formation is nothing but 2 electrons is required, isn't it? So total 8 electrons are required, 4 each, 4 pairs. 4 pairs electrons are required. It is nothing but 8 electrons. Now here 2 unpaired electrons is present and these 2 electrons are paired electron. 2 lone pair of electron is present and 2 unpaired electrons are present, but we require 4 electrons as unpaired electrons. So the excitation of the electron taking place from the 2s orbital into the 2p orbital. From the 2s orbital into the 2p orbital. Now the 2s orbital containing 1 electron, 2p containing 1, 2, 3. So total 4 electrons. So this 1s orbital and 3p orbital undergo Sp3 hybridization. So after the hybridization, mixed orbitals diagram will be 1, 2, 3, 4. So this is the Sp3 hybridized orbital. If it undergo Sp3 hybridized orbital, it forms a tetrahedral structure. After getting the tetrahedral structure, let me write the orbital diagram for the carbon. Carbon is at the center and 4 lobes. Sp3 hybridized orbital of a carbon atom. See the hydrogen atom, atomic number of the hydrogen is 1, it is 1s1. 1s1 refers to one hydrogen atom forming the sigma bond, another hydrogen atom forming the sigma bond, third hydrogen atom forming the sigma bond, fourth hydrogen atom forming the sigma bond. So for one carbon atom, 4 hydrogen atoms are present and the bond angle is for about 109 degree 28 minutes. Bond angle is 109 degree 28 minutes. So this is about the structure of methane with respect to the Sp3 hybridization, and these kind of questions will be asking for the final examination 3 marks. Explain the structure of or explain the hybridization present in CH4. That kind of questions will be asking for the final examination. Let me take one more example for the Sp3 hybridization. One more example for the Sp3 hybridization. Formation of C2H6. Formation of ethane molecule. Formation of ethane molecule. Carbon 6, 1s2, 2s2, 2p2. 1s2 2s2 2p2. Again, 2s2 2p2 is considered as a valence shell. So, if you write the box diagram, 2 electron and in the 2p orbital, 2 electron. If you consider the molecule in the C2H6, 2 carbon atoms are there, 6 hydrogen atoms are there. So 3 hydrogen atoms each for the 2 carbon atoms, and between the carbon to carbon single bond will be present. So for the carbon atom, total 4 single bonds are present, 4 sigma bonds are present. To form the 4 bonds, it requires 4 unpaired electrons. So the excitation of the electron taking place from 2s orbital into the 2p orbital. Now the diagram, 1, 2, 3, 4 electron. So this one undergo Sp3 hybridization. It undergo Sp3 hybridization. After undergoing the Sp3 hybridization, it forms a tetrahedral geometry. Now let me write the orbital diagram for the 2 carbon atoms. This single lobes overlap with each other. It forms a sigma bond, remaining 3 each. 1, 2, 3, 1, 2, and 3. And 6 this one hydrogen atoms are there. Hydrogen atomic number is 1, so 1 is 1. So 6 hydrogen atom overlapping with the hybridized orbital, Sp3 hybridized orbital of carbon atom. Sigma, hydrogen, sigma, hydrogen, hydrogen, sigma bond is formed, hydrogen, sigma bond is formed, So total, how many sigma bonds? 4 plus 3, 7 sigma bonds are present in C2H6. And here the bond angle will be 180 degree, but between the hydrogen is again 109 degree 28 minutes. So it is a second example for the Sp3 hybridization. Third example, formation of H2O. And this example in detail I have explained in the hydrogen topic. Structure of H2O according to the BSEPR theory I explained. It forms a tetrahedral geometry, but the shape of the water molecule is bent like a structure. Let us write the electronic configuration. Oxygen is 8, 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. 1s2, 2s2, 2p4. Okay. So 2s2, 2p4 is considered as an valence shell. 2s2, 2p4 is considered as a valence shell. If you write the box diagram, 2s orbital containing the 2 electron, and in the 2p orbital 1, 2, 3, 4 electrons. This one is a 2s, this one is a 2p. And the formation of the H2O molecule, for the 1 oxygen atom, 2 hydrogen atoms are required, and 2 hydrogen atoms are required means it has to contain, oxygen atom has to contain the 2 unpaired electron. It is already present, isn't it? So the excitation of the electron not taking place, but the hybridization taking place, because it is considered as a valence shell. So it undergo Sp3 hybridization. After undergoing the Sp3 hybridization, the structure becomes 1, 2, 3, 4, 5, 6. Sp3 hybridized orbital of the oxygen atom. Now, if you write the orbital diagram for the oxygen atom, 1, 2, 3, 4. Okay, and 2 hydrogen atom H, it forms a sigma bond. Another hydrogen atom, it forms a single bond, and it contains these 2 lobes containing the lone pair of electrons. So that H2O molecule hybridization is tetrahedral. Yes, geometry is tetrahedral due to the Sp3 hybridization, but the shape of the H2O molecule, it is an bent-like structure, and in the bent-like structure, we are expecting the bond angle in the tetrahedral geometry. We are expecting the bond angle as 109 degree 28 minutes, but instead of 109 degree 28 minutes, we are getting as 104 degree 5 minutes. Bond angle get reduced due to the repulsion between the bond pair and the lone pair of electron. Lone pair electron, and lone pair electron, and bond pair repulsion will be there within the molecule. So because of this repulsion, this one electrons which is present in the bonded pair, it almost we are getting the bent-like structure. So the bond angle got reduced to 109 degree 28 minutes to 104 degree 5 minutes. Next example is formation of NH3. Formation of NH3. Atomic number of nitrogen is 7. Electronic configuration is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. So total 7 electrons. And 2s2, 2p3 is considered as a valence shell. 2s2, 2p3 is considered as a valence shell. Now you need to write the box diagram. 1, 2, 3, 4, 5. Total 5 electrons, and here 3 electrons are unpaired electrons. 3 electrons are unpaired electrons. That electrons are used for the formation of the bond. See, in the NH3 molecule, 3 hydrogen atoms are there. To bond with the 3 hydrogen atom, it requires 3 unpaired electrons. Already 3 unpaired electron is present in the valence shell, as well it contains the lone pair of electron, isn't it? And this lone pair of electron and the unpaired electron which is present in the nitrogen, it undergo Sp3 hybridization. So during the Sp3 hybridization, 1, 2, 3 electrons. So it is a Sp3 hybridized orbital. If it undergo Sp3 hybridization, geometry of the molecule is a tetrahedral geometry. So during the tetrahedral geometry, nitrogen is present at the center, and 3 lobes we have to write, and 3 hydrogen atoms. It forms a sigma bond. 3 hydrogen atoms, it forms sigma bond, and on the lone pair electron is present on this lobe. So there will be a repulsion between the lone pair of electron and the bond pair of electron. So the bond angle will be reduced from 109 degree to 107 degree in the case of the ammonia formation. 109 degree to 107 degree in the bond angle in case of NH3 formation. And the shape of the molecule is pyramidal in the shape. Water is a belt-like structure. NH3 is pyramidal in shape. So these are all the examples for Sp3 hybridization. Next, next is Sp hybridization. Sp2 hybridization. Sp2 hybridization. In the Sp2 hybridization, one S and two p orbitals combining to give a Sp2 hybridization, where S character is for about 33.3% and P character is about 66.6%. Total 3 orbitals are involved in the bonding. One S orbital and 2 p orbital. One S orbital and 2 p orbitals are involved in the bonding. It forms geometry of the molecule is trigonal geometry. Trigonal geometry, and shape of the molecule is a triangular shape. Triangular shape or trigonal shape, if you say, is also correct. And the bond angle is 120 degree. Bond angle is 120 degree. Let me take an example for the formation of C2H4, formation of ethene molecule. 1s2, 2s2, 2p2. 2s2, 2p2 is considered as a valence shell. If you write the box diagram, 2 electrons in the 2s orbital, 2 electrons, isn't it? See, in the C2H4 formation, 3 sigma bonds will be present, 1 pi bond. Anyhow, carbon valency is a 4. So 4 electron has to be in the unpaired state. So the excitation of the electron taking place from the s orbital into the p orbital. 1 electron, 1, 2, 3 electron. Now the mixing of the orbital taking place, it is Sp2 hybridization. After mixing of the orbitals, 1, 2, 3 electrons, and this one is unpaired electron, and it is unhybridized orbital present in the carbon atom. Now if you write the orbital diagram for the 2 carbon atoms, one get overlaps with each other. Geometry is trigonal geometry. So it forms a triangular like structure. And how many hydrogen atoms? 4 hydrogen atoms. 2 to each. 1, 2. It forms sigma bond. 3. And the 4th hydrogen atom. And between the carbon to carbon, single bond is formed. It is a sigma bond. Okay. And I said valency of the carbon is 4, but 3 is satisfied. 1 more has to be satisfied by the unpaired electron or the unhybridized orbital of the carbon atom. It undergoes sideways overlapping. This one is a sideways overlapping. It forms the pi bond. See, these 3 bonds are the head-on overlapping. 1 bond, it forms the pi bond. It forms the sideways overlapping. So total 1, 2, 3, 4, 5. 5 sigma bonds are present. 1 pi bond is present in case of C2H4. So carbon undergo Sp2 hybridization. Second example, formation of aluminium chloride or formation of boron chloride also we can take. Boron fluoride or the boron chloride. And Pf3 structure already have explained. Pf3 structure already explained in the p-block element. Why Pf3 is acting as a Lewis acid? Because it has got the deficiency of 2 electrons. So the total electron around the boron atom is 6. It has to attain the octet electronic configuration by gaining the 2 more electrons. So Pf3 molecule is acting as a Lewis acid. Even aluminium chloride is also acting as a Lewis acid. Now let us write the structure of boron trifluoride Pf3 molecule. Atomic number of the boron is 5. 1s2, 2s2, 2p1. You try for the aluminium chloride. Okay. 1s2, 2s2, 2p1. 2s2, 2p1 is considered as a valence shell. If we write the box diagram, 2 electron in the 2s2 orbital and 1 electron in the 2p orbital. And formation of Pf3, 3 fluorine atoms required. For the 3 fluorine atoms, 3 unpaired electrons should be present in the boron atom. So the excitation of the electron is taking place from the 2s orbital into the 2p orbital. 1, 2, 3. So this one undergo hybridization. It is nothing but the Sp2 hybridization. So after the Sp2 hybridization, mixing of the orbital 1, 2, 3. Hybridized orbital, Sp2 hybridized orbital. So the geometry of the molecule is trigonal geometry. Now if you write the this one orbital diagram for the boron atom, boron is at the center, 1 lobe, 2 lobe, 3rd lobe. So total 3 unpaired electron, Sp2 hybridized orbital, geometry is trigonal. And now fluorine atom, this one atomic number of the fluorine is 9. Electronic configuration is 1s2, 2s2, 2p. 1s2, 2s2, 2p5, and 2s2, 2p5 is considered as a valence shell. So if I write the box diagram 1 to 2, 5 electrons, and in the 2pz orbital, it contains 1 unpaired electron that will be overlapping with the hybridized orbital of boron atom. So overlapping will be like this. Overlapping will be like this. So it forms a sigma bond for the fluorine, sigma bond for the fluorine atom, Df3 formation, and the bond angle is for about 120 degree. Bond angle is 120 degree. So these two are the examples for the Sp2 hybridization. Next, third kind is Sp hybridization. In the Sp hybridization, 1 s orbital and 1 p orbital. 1 s orbital and 1 p orbital, it is Sp hybridization where 50% of s character and 50% of the p character will be there. Now if I write the orbital diagram, spherical shape, s orbital is a spherical shape and p orbital is dumbbell shape. It forms, if it contains the two paired electron, geometry of the molecule is, what is the geometry of the molecule? It is a linear geometry. Sp hybridization, it forms linear geometry and the bond angle is 180 degree. So let me take an example for Sp hybridization. Let me take an example of Sp hybridization. First example is formation of ethyl. formation of ethane molecule. Atomic number of the carbon is 6, so the electronic configuration is 1s2, 2s2, 2p2. 1s2, 2s2, 2p2 is the electronic configuration for the carbon atom. If you write the box diagram 2s2, 2p2, 2s2, 2p2, 2 electron in the 2s orbital and 2 electron in the 2p orbital. During the formation of C2H2, only the 2 hydrogen atoms are there. One carbon atom, one hydrogen atom, another carbon atom, another hydrogen atom. But valency of the carbon is 4, so the excitation of the electron taking place from the s orbital into the p orbital. So during the excitation, 1, 2, 3 electrons. And these excited electron undergo hybridization. This hybridization depends upon how many sigma bonds are present. Between the carbon to carbon, 1 sigma bond will be present. Between the carbon to hydrogen, 1 sigma bond. So total 2 sigma bonds. So it undergoes Sp3 hybridization. Now after the hybridization, hybrid orbital diagram Sp containing 2 electrons, and these 2 are the unhybridized orbital. Now let me write the orbital diagram for the carbon atom. It forms the linear structure, isn't it? It forms the linear structure. Hydrogen atom, small the sigma bond, it is also sigma bond. Hydrogen atom, it also forms the sigma bond. So total 2 sigma bonds got over. Now we need to represent the unhybridized orbital of the carbon atom. Unhybridized orbital of a carbon atom. It undergoes sideways overlapping. It undergoes sideways overlapping. It forms a pi bond. So total 2 pi bonds are formed. 1 sigma bond is formed between the carbon to carbon. Carbon to carbon, 1 bond is a sigma bond. Another 2 bonds are the pi bonds. And the bond angle is 180 degree in case of C2H2. Another example, BeCl2, beryllium chloride formation. BeCl2 formation. Atomic number of the beryllium is 4. So the electronic configuration is 1s2, 2s2. 2s2 is completely filled, but during the formation of the beryllium chloride, it requires 2 electrons, isn't it? 2 unpaired electron is required. So the electron which is present in the valence shell undergo excitation. See, the 2s electron is present in the valence shell, 2p is 0 now. During the excitation from the 2s orbital to the 2p orbital, excitation taking place. 1, 2 electron. And these 2 unpaired electron undergo Sp hybridization. After the Sp hybridization, electrons will be like this. If it undergo Sp hybridization, geometry is linear geometry. Later on we'll study about the structure, I mean the shape of the molecule. Now let us write the orbital diagram of the beryllium. Orbital diagram of the beryllium. Okay. Next, in the beryllium, chlorine atom is present. Chlorine atom atomic number is 17. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. 1s2, 2s2, 2p6, 3s2, 3p5. And 3s2, 3p5 is considered as a valence shell. In the 3p5, 3pz containing 1 electron, and the rest of the 2 orbitals, that is 3px, 2 electrons, 3py, 2 electrons, 3pz containing only 1 electron. That electron gets shared between the beryllium atom and the chlorine atom. Beryllium atom and the chlorine atom, it forms the sigma bond, and the bond angle is 1 of the 180 degree, and the shape of the molecule is linear. It is linear in shape. I hope all the points are cleared, and out of these molecules, one will be asking for the 3 marks. Still 2 more times I need to explain, but out of these 2 will be asking for the examination. And one more thing, important questions, nothing but repeated questions for the final examination of different districts. We have listed out the questions with the answers. We are sending through the group. Please go through the questions and the answers. As well, in the group, assignment questions are given. Assignment questions of all the chapters. I think redox reactions, hydrogen chapter, S block elements, P block elements, already you got the hard copy. Now through the group we are sending the soft copy, PDF format we are going to send for the chemical bonding, some basic principles and techniques, as well as I think, I don't know about the redox reaction, we have taken it or not, still we are sending all these questions, assignment questions. Please go through the questions, because these assignment questions are also they are given like it is also an repeated questions from the different states. Please go through the question and try to answer it. And we are going to conduct the final examination also. Maybe by that time these questions will be arising. Next, hybridization involving d orbitals. Hybridization involving the d orbitals. Hybridization involving the d orbitals. See, till now we have studied about the Sp3 hybridization, Sp2 hybridization, and the Sp hybridization. 3 hybridizations you have studied. Only the S and P orbitals are involved in the bonding. But now we are going to study about the orbitals which is involved in the d orbitals. I said during the hybridization, mixing of the orbital taking place. Why this mixing of the orbital taking place? Because the orbitals have got different energies. Different energy in the sense, S orbital have got less energy than P orbital, than D, than the F orbital. S orbital have got less energy than the P orbital, than the D orbital, than the F orbital. Now we have studied about the mixing of the S and D. Because nearer energy orbitals mixing taking place. Now we are going to study about the mixing of the d orbitals also. So S orbital and the d orbitals with the different energies, isn't it? Different energies. Even S will be mixing with the d orbitals also. But the condition that d orbital energy, that d orbital should be present in within the same shell. It's like, see, if you write the electronic configuration, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, and 4d. Excitation of the electron taking place from s orbital to d orbital within the shell. ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಎಕ್ಸೈಟೇಷನ್ ಆಗುವಂತದಲ್ಲ. ಇಟ್ ಈಸ್ ನಾಟ್ ದ ಮೆಥಡ್ ಟು ಎಕ್ಸೈಟ್ ದ ಎಲೆಕ್ಟ್ರಾನ್, ಬಿಕಾಸ್ within the same shell orbitals are present. That orbitals have got somewhat similar energy, so that the excitation of the electron from the 3s orbital into the 3d orbital is okay, because the energy difference between the 3s and 3d is less. and excitation of the electron from the 4s orbital to 4p orbital taking place because the energy will be somewhat similar. So the excitation will be taking place from the s orbital into the d orbital. ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಎಕ್ಸೈಟೇಷನ್ ಆಗುವಂತದಲ್ಲ, within the shell itself electrons can jump from one orbital into the another orbital. So we are going to study about one example for the this one hybridization involving the d orbital, Sp3 hybridization. Sp3 hybridization where one s orbital, 3p orbital and 1 d orbital, it forms a Sp3 hybridization. If you write the orbital diagram, circular shape, S, 3p orbital, x axis, x, y and z, px, py and pz, and I am going to mix with the dz orbital, dz square, and all the orbitals are considered as a degenerate orbital, so that we can mix with the dz square also. After the mixing of the orbital, 5 lobes should be formed. So it is forming the pi lobes, 2 upper side, 3 lower side. So it is forming the Sp3 hybridization. Next example for the formation of a phosphorus pentachloride PCl5 formation. Atomic number of the phosphorus is 15. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3. 1s2, 2s2, 2p6, 3s2, 3p3. 3s2, 3p3 is considered as an valence shell. So if you write the box diagram, 3s containing the 2 electrons and 3p3 containing the 3 unpaired electrons. 2 electrons and 3 unpaired electrons are present in the 3p orbital. Now, see, during the formation of the PCl5, 5 chlorine atoms are required, isn't it? 5 chlorine atoms means 10 electrons is, 5 unpaired electrons should be there. But here only 3 unpaired electron is present. So from the 3s orbital into 3d orbital, excitation of the electron taking place. Excitation of the electron is from the 3s orbital into the 3d orbital taking place. 1 electron in the 3s orbital, 1, 2, 3, and in the 3d orbital only 1 electron. Now it undergo Sp3 hybridization. After undergoing the Sp3 hybridization, box diagram will be like this: 1, 2, 3, 4, 5 unpaired electrons present together. If you write the orbital diagram for the phosphorus atom, 5 chlorine atoms are there. 5 chlorine atoms is nothing but 3s2, 3p5. 3p5 containing the 3pz 1 orbital. So the overlapping will be like this, head-on overlapping. All the bonds are sigma bond formation, sigma bond formation taking place. So 5 chlorine atoms. Okay, so if it undergo Sp3 hybridization means what is the geometry? It is a trigonal planar geometry. Trigonal planar geometry where phosphorus atom is present at the center. Chlorine atom in the triangular shape. One is above the plane, another one is below the plane. Trigonal, not the planar, sorry. Trigonal planar means Sp2 hybridization trigonal bipyramidal. Trigonal bipyramidal is this one hybridization geometry of the Sp3 dehybridization, and this is the structure of PCl5. Hope all the points are clear now. Now let me go with the another type. Another example involving the second one is Sp3 hybridization, where 1s 3d and 2d forms Sp3 hybridization. Sp3 hybridization. If you write the orbital diagram, P orbital dx dy dz, 2d orbitals we need to write it now. Dx square minus y square now after mixing three lobes above, three lobes below. So it forms a octahedral geometry. Octahedral geometry. It forms the octahedral geometry. Where the three lobes is present above the plane, three lobes are present below the plane. If I take an example of SF6, sulfur atomic number is 16, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. 3s2, 3p4 is considered as a valence shell. 3s2, 3p4. But during the formation of the SF6, 6 unpaired electron is required. Here only 2 unpaired electron is present. So from the 3s and from the 3p, excitation of the electron is taking place into 3d orbital. Now the box diagram becomes 1, 3, 4, 5, 6. Mixing of the orbital taking place, it undergo Sp3 hybridization. Hybridization. Now, Sp3 hybridization means it forms a octahedral geometry. Now, let us write sulfur at the center. Sp3 due to hybridization. 6 fluorine atoms are there. 6 fluorine atoms is nothing but 2s2, 2p5, where 2p is that containing 1 electron. So overlapping taking place like this. F, it forms a sigma bond. F forms a sigma bond. Forms a sigma bond. Forms a sigma bond. If you write the structure, with the equal distance fluorine atom. So this is the structure of a SF6. It forms a octahedral structure. So that is the formation of SF6. So out of all these structures, one will be asking for the examination for 3 marks. Write the explain form. Otherwise, write the structure of the credit, whatever it will be asking for the examination. Next, polarity in a covalent bond. Polarity in a covalent bond we need to study. We know that covalent bond is formed due to shared pair of electron. Due to shared pair of electron or sharing of electron taking place between the two atoms is nothing but the covalent bond formation. After sharing of the electron, that is during the formation of the covalent bond, after sharing of the electron, one of the atom after the formation of the molecule, one of the atom within the molecule attracts the shared pair of electron towards itself. So when it attracts the electron towards itself, it forms the two ends. One is positive end, another one is a negative end. So covalent bond acting as an polarity in nature. Covalent bond shows the polarity in nature. Actually, polarity bond will be showing only in the ionic bond, because ionic bond is formed by complete transfer of one or more electron from the valence orbital of one atom into the valence orbital of another atom. So the charges will be occur during the formation of the ionic bond, but during the formation of the covalent bond, sharing of the electron taking place, isn't it? But after sharing of the electron, electrons get attracted towards itself. Now let me consider two examples, A, B and A2 are the two molecules. A and B, in between two bonds, single bond is present. Sorry, in between the two atoms, single bond is present. Let me write the electron between the two, mid of the two. Single bond is formed between the A and A atom. Now consider B atom is electronegative, so that than the A atom, so that the shared electron towards itself, shared electron attracts towards itself and ಸ್ವಲ್ಪ ಅದರ ಹತ್ರ ಹೋಯಿತು. Now A atom lost its electron, not completely lost its electron, so it gets the partial positive charge. B gained the electron, it gets the partial negative charge. So we are representing A and B as the arrow mark like this. This arrow mark shows that shared pair of electron between the A and B get attracted towards the B. So B carries the partial negative charge, A carries the partial positive charge. Now, if you consider these two examples, these two atoms have got similar electronegativity character, isn't it? Both atoms are same, so that this shared pair of electron will be present at the center only. So there is no partial charge, there is no partial positive charge, there is no partial negative charge. So we can conclude that if a homonuclear diatomic molecule molecules will not shows the polarity in the molecule, will not shows the polarity. It forms a covalent bond, but it is not showing the polarity in the nature. But dinuclear or the different nuclear diatomic molecules shows the polarity in the molecule. And this charge separation, let me take an example, hydrogen chloride and H2 formation. Between the hydrogen single bond is present, between the H and the Cl single bond is present. That electron I am writing at the center, but chlorine is the electronegative element. It attracts the shared pair of electron towards itself. So hydrogen carries partial positive charge, chlorine carries partial negative charge. Okay, so charge separation occurs. This is nothing but a polarity formation within the covalent bond molecule. That polarity can be calculated using the magnetic moment. And this magnetic moment is represented by mu is equal to E into D. E is nothing but the charge. D is nothing but the distance between the two atoms. Is nothing but the D. E is nothing but the charge on an atom. So mu is equal to E into D. And this one magnetic moment SI unit is D by. It is nothing but the D. So it is measured in terms of D by. 1 d by is equal to 3.335 into 10 to the power minus 30 coulomb meter. D by is the SI unit of magnetic moment. 1 d by is equal to 3.335 into 10 to the power minus 30 coulomb meter. Coulomb refers to the charge, meter refers to the distance. Okay, so it is nothing but the measurement of the dipole moment within the molecule, and this will be asking for 1 mark. Even it is important for the competitive part. Let me give 2 examples. Formation of hydrogen fluoride. What is the magnetic moment of the hydrogen fluoride? We need to calculate it. Fluorine is the electronegative one, hydrogen is the electropositive one. So that electrons get attracted over here. It forms the net overall charge or the magnetic moment on the hydrogen fluoride is not equal to 0. Is not equal to 0. Next, carbon dioxide. In the carbon dioxide, C double bond O, C double bond O. We know that oxygen is the electronegative, so attracts the electron towards oxygen side at the both ends. So the net magnetic moment mu is equal to 0. Here mu is not equal to 0. Akadenu eliyutte, ikadenu eliyutte. So the net dipole moment for the carbon dioxide will be 0. If I take an example of H2O, Oxygen containing the two lone pair of electron and the hydrogen atom. Oxygen is the electronegative element, so attract the electron towards the oxygen atom. Oxygen itself containing the lone pair of electrons, so the net dipole moment in the opposite direction. So nu is not equal to 0. In case of NH3, lone pair of electron is present on the nitrogen atom. Towards the nitrogen it attracts net dipole moment in this direction. So nu is not equal to 0 for the NH3. Let me take another example. PCl5. Phosphorus is present at the center and chlorine atom. Five chlorine atoms. We know that chlorine is the electronegative one, so it attracts towards itself. Isn't it? Polarity will be there, but on both equal sides chlorine attracts the electrons towards itself. Therefore, net dipole moment on the phosphorus atom is equal to 0. So this is how to calculate the magnetic moment for the given molecule. Next, ionic bond behaves as a covalent bond. Ionic bond acts as a covalent bond. Ionic bond is nothing but complete transfer of one or more electron from one atom to another atom is nothing but the ionic bond formation. So during the formation of the ionic bond, A plus B minus equals to AB. Isn't it? That is the ionic bond. After the formation of the ionic bond, these molecules acting as a covalent bond. It shows the covalent bond. It is due to size of an atom. See, consider this is an A atom with a smaller atomic size, B atom with the bigger atomic size. Okay, positive charge at the center, electrons are revolving around the nucleus. Now, due to the polarization is nothing but the positive charge which is present in an atom, cation, attracts the electrons of the negative ion. So that it forms the polarity. E formation of the negative charge over here, positive charge over here. Polarity occurs in the negative ion. Due to the polarity of the positive ion, it attracts the electron towards itself, so that polarity occurs between these two. Okay, so due to the polarity of the molecule, ionic bond, then it is acting as a covalent bond. It is nothing but after that sharing of the electron, mutual understanding between the two atoms taking place, mutual sharing of the electrons or mutual attraction of the electrons taking place between the two atoms. It is nothing but the polarity. Now, this polarity of the bond or acting the ionic bond as a covalent bond is explained using the Fajans rule. Fajans rule says that when a size of cation cation should be smaller. It should be smaller and size of the anion should be bigger. Then only ionic bond is acting as a covalent bond. Cation size is very small, anion size is a bigger one. So that cation, a positive charge, attracts the negative charge of the anion. It will be like this: smaller ion, bigger ion. Polarization occur. Negative charge over here, positive charge over here. Polarization occurs, so that force of attraction occurs between the cation and the anion. Ionic bond is acting as a covalent bond. It is nothing but the Fajans rule. When the atomic size, cation size is a smaller one and anion size is a bigger one, ionic bond is acting as a covalent in nature. Or the second factor is charge on cation is larger, charge on cation is larger than the charge on anion. Like Al3 plus acting as a more positive in nature than Ca2 plus than Li plus. So more the charge, greater the charge on the cation, greater is acting as an ionic bond into the covalent bond. So it is about the Fajans rule. According to this, ionic bond is acting as a covalent in nature. I hope it's clear. Next, three more terms I have to explain: formation of the coordinate bond, formation of the hydrogen bond, as well as the MOT. We finish all those things. Chemical bonding chapter will get over. If I start with the hydrogen bond, I cannot finish. So let us continue with the next class. Thank you.